Okay, here's the E&M lectures. I'm doing this from the barn tonight because I had some stuff to do and I wasn't able to get it done at work. We're going to talk about, for this lecture, electromagnetic waves in a vacuum. We talked about electromagnetic waves, a little bit what they are. Talked a little bit about waves, direction of travel. We talked about polarization and just waves themselves and the wave equation and all that rigmarole, right? That's an old word for you. So what I want to do now, though, is talk about these waves in a vacuum. So these waves this really came out of Maxwell, did the analysis. So 9.2 electromagnetic waves in a vacuum. And 9.2.1 is the wave equation in the electric field and the magnetic field. Now, what Maxwell basically put together, he took Ampere's law, added a little bit to it, something called a displacement current. Basically, tells how current is forming. You have a changing magnetic field, you can get ripples of current and stuff. So what we want to do is start off with, in a vacuum, there's no charge and no current. So let's look, if you take regular Maxwell's equations that we've done before, but no charge, no Q, no I. So that's why he's looking a little weird. No Q, no I. With no charge or current, Maxwell's equation look like, and this is what happens when there's no charge nearby or some current nearby. You've got this wave traveling. It seems like there's some wave traveling. What governs it? Well, del dot E equals 0. That's Gauss's law. Del dot B equals 0. That's with the current in it normally. Remember we look at dot products and cross products. Del cross E equals minus partial B respect to T. And that's a changing magnetic field creates an electric field. And del cross B says mu naught epsilon naught. You get the partial of the electric field with respect to time. So changing electric field creates a magnetic field. And you see from Maxwell's equations also why I harp so much on dot products and cross products. You got to understand what they mean conceptually to get this. So this is del dot. So how much is it changing in the direction of the electric field? How much changing in the direction of the B field? Well, if there's no charge or current, it's not changing. There's no rate of change of it. Okay. Now it said these are together. They equal each other. So these are coupled first order, which tends to be easier to solve. But there's partials here. They're partial differential equations. Now some would say, oh no, that's bad. But really, that's just decent. I mean, first order is easier to solve than second order. Let's try decoupling these and get these separate, because it's not, when you got B's and E's, together, it makes life more difficult. So let's decouple the del cross equations. So to do that, what we've got to do, let's look at the curl here and here. If we apply the curl to both of these, so we're going to do del cross, del cross, del cross, del cross. Not del Earnhardt, but del cross. All right. So del cross E. That goes back all the way to the beginning of the semester, right? We forgot all that. The COVID crap. Oh my goodness. Yeah, but go back very beginning, first chapter. This equals del times del dot E minus del squared E. Then all that would equal, on this side, del cross this. So remember, just like in algebra, what you do to one side of the equation, you got to do to the other. Same thing holds. Same thing holds. Okay. All right, so and they say from this, that off the top of my head, honestly, it just doesn't follow. But doing the del cross here, they pull the partial respect to t out of it since that's not a function of it. So let's pull that out. Minus, I'm going to put this on this side. I'm going to pull out the partial respect to t because it doesn't change over the del cross because the del is a function of position, not of time. So I'll be partial respect to t, pull the minus out, del cross b, and what do we know del cross b is equal to? Well, what do you know? Del cross b is equal to this. Well, if there's a negative in front of this one, well, del cross b is that. So what I can do, wherever I have a del cross b, I'm going to put that in there. So I'm going to plug in for right here. I'm going to plug in right here. That's minus partial respect to t, mu naught epsilon naught partial e respect to t. Well, I can run that inside if I want, because it, it just gives a double one, because I can multiply it inside now. That's just been factored out. You can think of it like that. Minus mu naught epsilon naught partial squared e with respect to t squared. So I got a second derivative, partial second derivative. Okay. So del cross b is this. And they do the same thing to the other one. They get something very similar. And when they get something similar, they end up, and for board space, I'm just going to say what they end up. You end up with, after doing the same to del cross b, do the same here that you did there. If you do that, you end up with, and that's assuming, I'm going to put, because it's del dot b, see you got del dot e right here. What do we know del dot e is equal to? Del dot e has to be 0. Well, what's, del 0, it's 0. So that term just goes away, and we're left with this del squared term. So we get a del squared term here. It's going to equal basically this. Because this term here, we stick that in there, and we get this out of it. Maybe that's something good to do on the test, make it on the final, right? To put that on there, finish this derivation. And you get that del squared e equals mu naught epsilon naught partial e squared with respect to t squared. And that del squared b, the b field, is equal to mu naught epsilon naught partial squared b with respect to t squared. We now separated this, because now you had to know b to find e, you had to know e to find b. Well, now you have these separate now. You don't need b to find the electric field. As long as you know the second derivative of the electric field with respect to time, you can find how much basically the Plossian of it. It's the second derivative of position. Now, this is a second order partial differential equation. Are they a little bit more harder to do? Yeah. But, like the book says, it's the price you pay for decoupling these. Now, what's interesting with this, in a vacuum, that's where this mu naught epsilon naught is. Basically, you can generalize this to say then this can give the three-dimensional wave equation. What is that three-dimensional wave equation? That's how E changes as it goes forward. This is how B changes in position as over time as it goes forward, as it moves forward. How much does it change? It's a second derivative of it. And that is that del squared F equals 1 over V squared partial squared F with respect to T squared. And why did I put V there? So what we found is that this is how much the wave changes as a function of time. This is how much the wave changes in position. So this would be the magnitude of that wave over time. This is how much the wave changes with position. This term here, this V squared, V is actually equal to, because we can say here to here, 1 over V squared equals mu naught epsilon naught. Well, if I run that here, put that over there, it's basically switch them and take the square root to get rid of the V. So the velocity of an electromagnetic wave is a function in a vacuum, is a function of two proportionality constants. Permittivity of free space and the permeability of free space. These are just proportionality constants that we got from, basic stuff that was done at the very beginning of trying to understand this. And those actually come back and get to us. So what does that tell us then that things, that these traveling electromagnetic waves, we can predict the velocity of it. And what's really, really cool, when this was really, really found out just in the really, really beginning, this velocity was really, really close, I think, by Romier's work with the spinning, he had spinning mirrors and stuff. This was the speed of light. Darn close to it. And as they did more and more refined experiments, that was the speed of light. So they were like, wait a minute. If the speed of light is this, and the only way if the speed of light is equal to this V, this value, that means light must be comprised of what two things? Electric fields, magnetic fields. It's got to be electric and magnetic fields. And what is it? It's a rate of change. These things are oscillating up and down as it's moving forward. Now, it's hard to really see that. I'm going to get to that here in just a minute. But that's really cool. And by the way, what is this value? You probably know it's 3.00 times 10 to the 8 meters per second, which is about 186,000 miles per second. Light travels. As light moves, as the light, shining above from the fluorescence above me, as light hits me and goes to the camera, it's moving at 186,000, actually 280, let's just say 186,000 miles per second. When you see, with thunder, what was the old saying? Lightning McQueen, thunder always followed lightning, all that, ka-ching, whatever. You have a delay from thunder when you see the lightning because, the thunder is the air rushing back in and then it has to take time to get to you. You don't see that time delay with light in most situations. On the Earth, we don't. The Earth is, about 25,000 miles around? Or about 25,000 miles all the way around at the equator. So that's going around the Earth 7.5 times, or a little bit more than 7.5 times a second. which is crazy talk, right? So on the Earth, we never noticed them. It just seems instantaneous, like that. Galileo tried to do some experiments where, he would have some guy would uncover a lantern, he would see it, he would uncover his lantern. The other guy, once he saw Galileo uncover his lantern, he would basically stop a clock. So he'd turn a clock on when he would uncover his lantern, and they would be miles away, on top of places at the dead of night, so you can see a long distance. So it might be 10, 20 miles away. And by the time he would see it, he thought he could, light should have an ability, every 10, 20 miles back total travel. You should be able to get a little delay, maybe even half a second or something like that. But no, he couldn't. It was within the time. It was instantaneous. They never could get a time. It was within their ability times, to uncover their lamps. That's because it's traveling so freaking darn fast. 186,000 miles per second. We really only see the effect of the speed of light when we deal with astronomical things, because their distances, this isn't that fast from here to the sun. We're 93 million, approximately, not on average, what is it, about 93 million miles away from the sun. It's elliptical, so it changes a little bit. What's interesting is, it takes light about 8.5, 9 minutes to get from the sun to us. So when we're looking at the sun, we're looking at how it looked 9 minutes ago. Sun could have blew up. It could have been dancing. Yeah. No, it's not. But if it could be, and we wouldn't know it till 9 minutes later. When we look at the stars at night, I'm doing this at night and everything. We look at the stars, we're looking backwards into our universe. We're seeing what happened 20 years ago, 50, a million years ago. For, if something's a million light years away, I don't know if we see anything with our eyes a million light years away. I don't know if anything's that bright. Galaxies may look like stars, or they'd be very faint, Andromeda. So you'd be, that's what, I think that's about 400 or so thousand light years away from us. I think I'm probably off by about 50%, 60% there. But that's pretty darn amazing. That's how fast light travels. And it's all because that's how much space-time itself that Einstein came up with, that's how much space itself allows, when there's an oscillation in the electric field, how easily that travels through space itself. How much a magnetic field, how easily it can travel through space itself. And like ripples on a water, and ripples will go out, from water. A radio antenna is the same thing. It just sends out electromagnetic field, say an E field this way. So the E field goes out and comes down, it affects things beside it, and it just travels on. Because it basically warps space a little bit, just like doing that on a top of the water on a pond or something would cause ripples to form going out. Pretty cool. All from Maxwell's equations, we're able to show where there's no charge and current, which is what happens when we're not near anything like that, just traveling through space. We can find the speed of it just from those proportionality concepts. That's pretty cool. Let me wipe the board, and then we're going to talk about monochromatic plane waves. Let's see how well this does. I'm going to leave the video on as I wipe this, so you can watch me in my almost futile effort to do it without using acetone. Aha! And how acetone definitely is a solvent. It definitely is a solvent. And how I need to get more of these. You don't try to want to get acetone inside you. See, I try to use a lot so I don't get it inside me. It'll absorb right through the skin. The way these things hurt you is that, if I'm not mistaken, they basically get absorbed and they take the place of oxygen. That's why these things will give you a high. And they take the place of that oxygen. I mean, that's not good to brain. Okay. See, it's coming off. Give me some more acetone soon. I did this for 2 weeks. See, I go through napkins pretty quick. All right, this is about good enough. All righty. All right, let's look at, I'll use some different colors. Monochromatic plane waves, 9.2.2. Monochromatic plane waves. Well, monochromatic means there's one, mono is one, chroma is color, one color. So let's call this will be a single frequency. In other words, the wave is going to have one frequency. When it's a plane wave, you can think of it like as a sheet of paper. And we'll do a drawing here. This is my little napkins I use. So a plane wave, it's plane across. It's just simple. It's just average. I have a kitty cat. We call her Katie. And Katie's not here. Chloe's around here somewhere. She was. I was holding her earlier. But we call her Basic Cat. Why we call her Basic Cat? Because she's just basic. She's just gray striped, a little bit of orange, but she's just personality. She's just basic. Well, a Basic Cat would be a plane wave. Plane waves just go like this through space. You can think of it as, you can almost think of it like a laser creates a plane wave, but normally that's dealing with phase. This thing doesn't have to be in phase. Plane waves just have to be the same. They're just kind of all going forward at the same, with the same. And so same frequency. It's like a sheet of light. Think of it as a sheet of light just going forward, a plane wave. None of it's getting in front of the others, traveling at the same velocity and stuff like that. That's a plane wave. All right. So we draw it up here. A plane wave. We'll call this Z, call this Y, call that X. A plane wave will just be in sheets like this. And it's traveling in this direction. That's the direction of the velocities in that direction. Now the electric field, as it goes, as a function of time, remember we said that solutions of the wave equation are cosines, sines and cosines. So the electric field over time, say on this one, it's getting bigger. On this one, it started getting smaller. So now it's getting smaller the other way. And if I drew another one in, it would get bigger that way, and then it would just go back and forth and oscillate. So as it propagates forward, this electric field starts big, gets small, gets big, gets small, then gets big in the downward direction, I should say. And big in the upper direction, big in the downward direction, big in the upper direction. So over time, that's how it goes. Okay? Now, what we can say here, and remember we said solutions to the wave equation are sines and cosines. I also said that we can think of sine and cosine in terms of imaginary exponentials. Grown appropriately, as you did in class, or wanted to. But yeah, that's what we got to deal with. And they're not as hard as you think, though. We're going to get really deep into it. Well, so we can say the electric field, as a function of z, as it moves, and time, is going to be the magnitude, and this magnitude here is a complex magnitude. Okay, it's a complex magnitude there. And e to the I, in this case, kz minus omega t. Z is just a direction of motion. Omega t, remember this to be the argument of that sine function that we talked about earlier, we derived previously. And one thing it says, for to do it this way, it's a complex magnitude. To get what the actual amplitude of the wave is, we have to take the real part of the complex number. And you remember how to take real parts of complex numbers? You know, E star was how you get the real part of it. The real part, it's just times you take a complex number times its complex conjugate. Let me put this up here. To find the real part of a complex number, I'll say do A star. So we'll let A equal, we'll say x plus IY. And if that's true, then AA star would be x plus IY times x minus IY. And if you use the FOIL method, remember first outside, inside, last, you get x squared. This would give you x squared. Here, outside is minus xi plus ixy. So those will cancel. Minus I squared y squared. Okay. And if you have that, those cancel. Well, I squared is negative 1. Negative 1 times negative is a positive. That will give you x squared plus y squared. And this is the real part of x plus IY. Don't you love complex numbers? Okay. All right. So now that you guys are grown and not mad at me, and I went over some math, but that math you may need to do. Oops, I hear the dog barking. My wife must be coming home from work. Now, what we can say is, because del dot E equals 0 and del dot B equals 0, the dot product here. So as it's moving forward, the electric field, the complex part of that, basically, that complex magnet going forward is 0. It's 0. So there's basically the E field in the Z direction. It's got nothing in Z. It doesn't, the E, I drew it nothing in Z, but this, if you apply this to this complex value, if to do that, then the Z component of, because there's a component in Z and in T here, because it's just the rules of complex numbers with complex amplitude. This has to have a little bit in this, because you could break this up. Remember, multiplying exponentials add exponents. So you could have an exponent with kz in it and a coefficient in front, and omega t, I omega t in front with a amplitude. So each one of these terms here, ikz, iwt, as the argument for that exponential, has an amplitude, has a coefficient in front of it, which is an amplitude of it. Well, the one for the ikz argument of the exponential, that would be the z component of this. It's 0. Because in that direction, and remember the del is in this case, z direction only. To make that be true, for this to be true, then the amplitude's got to be 0. That's the only way. Because when you do that, that basically means that derivative, it doesn't change any in that direction of motion. Since it doesn't change any in the z direction, it doesn't change any. I mean, you could say, well, it's a constant value, but there's an old saying with how, if you got a constant without loss of generality, you can call that constant 0. That's what they do here. Okay. And the z component, and then the z component of b naught equals 0 for here. So in reality, what you've got is that b naught and e naught are only in directions perpendicular to z, and that would be x and y. Be x and y. Now, if you remember, I'll say, but del cross E, we said, remember this is one of Faraday's. This is Faraday's law. Del cross E is how we get electromagnetic induction. Del cross E is minus the partial of the B field with respect to time. So a changing B field creates an electric field. That's what this is saying, electromagnetic generation. Well, if that's true then, and we apply it up here, what you find is that minus K times the Y component here equals omega times the X component there. And the same so this constant, remember that was that wave propagation. So the wave propagation constant, the K variable, wave number they call it. You've got a relation between the X component of B and the Y component of E, the Y component of B and the X component of E. So it's like they're equal, but they're in the opposite direction, I should say orthogonal directions. One's in X and one's in Y. And you can write this if you want, because all they did was take this and apply it here, apply it to this. And of course I didn't write this up here, my apologies. There's a B field version of this. B of Z and T that equals B naught E to the I KZ minus omega T. And that's what you're applying. You stick these in here. You stick those in there and do the math. This is what you'll get out of it. And you think about cross product is where this comes from. Remember when you do the cross, because you got to do the, you set up the, what's it called? When you do the cross product, set up the little terms there, X, and then you do the, that minus that, set them up. That's the way you set those up, and that's where the different directions come at there. Now, or you can write this as B naught in the